Trend models. First of all, let's look at the broader definition of a time series. A time series is a variable that's observed over time. For example, if we're looking at the earnings per share for a company over the last 10 years, the earnings per share in this context would be regarded as a time series. And there's the giveaway right there, because we're observing that variable over the last 10 years. Now, what are some of the variations of trend models? And what a trend model does is it tries to establish a relationship between the time series variable and time. So the first trend model is referred to as a linear trend model. For example, in this context, sales would grow by constant amount over time. So we're plotting sales here. This would be dollar sales, and here's time. So the time series function would be as follows. So sales at any point in time is equal to B0, which is right there, plus the slope, and we identify the period for which we are making the observation, and it's right there. And B1 in this context would represent dollar change in sales per annum. So over here we have total sales, but if you're looking at B1, which is the change per period, naturally that would refer to change in sales, let's say per quarter or per year. Now the other variation of a trend model is log linear trend model. And in this context, sales would be growing by constant rate or percent over time. Now here's the tip that I have for you, because you're going to see log or logarithm throughout the whole curriculum, right? So do yourself a favor. Whenever you see log, just think percentage change. And what's the twist in this context? This percentage change is measured using continuous compounding. So once again, whenever you see log, don't panic. Just say, oh, they want to know what the percentage change in sales is, compounded on a continuously basis. And of course, I'm going to give you an example. But first of all, I do want to show you some ground up tools that'll help us navigate through this, right? Once again, visuals is a very powerful tool because it gives you the big picture. And notice that in this case, we're plotting the lawn of sales. What does that mean? We're plotting the percentage change in sales. But in this scale, though, we're looking at the percentage change in cumulative sales. And here's time, right? Because it's still a trend model. So the equation of this function would be the ln of sales, which is right here, is equal to B0. So do you see how it's the same format as a trend model? The only difference is instead of just plotting sales, we're plotting the percentage change in sales, right? And there it is again. So there's our B1, which is our slope. And of course, we would have to identify the point in time that we're making this observation. However, now B1 tells you what the percentage change in sales is per period. So once again, I just want to show you the contrast between trend model and log linear. With trend model, we're plotting total dollar sales. With the log linear, we're plotting the total percentage change in sales. The B1 here, the slope, tells us what the dollar change in sales is per period. But the B1 here, because it's a log model, it's telling us what the percentage change in sales is per period. So it's the exact same template, it's the exact same framework, right? The only difference is instead of plotting dollar sales, we are plotting percentage change in sales, okay? And here's the example that I promised you. Suppose that we're told that the discrete growth rate in sales is 10% per annum. What does discrete mean? It's the growth rate without any compounding. So this is just the annual rate. Think of it this way, compounded just once. So step one, because we're using a log linear model, and how do we know we're using a log linear model? Well, are they giving us dollar sales or percentage change in sales? Remember that trick I showed you? Make that association between percentage change and logarithms, right? So whenever you see logs, think percentage change. And whenever you see percentage change, think logarithms. So that's how I knew that I have to set up a log linear model. Well, if I'm using a log linear model, what was that other advice I gave you? With log models, when you're calculating percentage change, it's done on a continuously compounded basis. So that's our step one. Let's find out what the continuously compounded growth rate is. So the equation we're going to use to transform from discrete over to continuous is this one right there. So you could see it's not a big deal. So I don't mind asking you to maybe just memorize that. I mean, there's not much to it, right? It's a little bit of calculus, right? So we plug in the discrete rate, and so I'm just taking it step by step. So we get e to the x is equal to 1.1. Now to get rid of the e, we take the logarithm of both sides. So the logarithm and the e cancel each other out. And over here, we just calculate the ln of 1.1. So then you get x here. And when you punch in 1.1 and then hit the log button on your calculator, you get 0.0953. So the way to read this is 10% discrete growth rate is equivalent to a continuously compounding growth rate of 9.53%, right? These two numbers are equivalent, ladies and gentlemen. But because we're using a log model, we have to use this version. That's the way you really should see this, is that it's a formatting issue. So we have to go from discrete to continuous, but they both represent the same variable, which is the percentage change in sales per annum. Okay. So since it's per annum, this would be your beta 1 coefficient, because remember what we said about beta 1, the slope? It represents the percentage change per period. Step 2. Let's suppose that the intercept is given to us as 3.7, and we're asked to calculate what sales will be at t equals 20 years. Now here's where you have to be a little bit careful. Are they asking for total percentage change in sales? Or are they asking for sales? They're two different things, right? They're asking for the dollar sales, because I don't see percentage change there, right? So that's what we're going to find out. So here's our template for the log linear trend model. So ln of sales, which means the total percentage change in sales, is equal to that. And we were given the values for the beta 0 coefficient and the beta 1 coefficient. And we're told that we're looking at year 20. So there it is. So you calculate this whole thing. So the ln of sales is equal to 5.606. And you have to be careful. This 5.606 could very well be a decoy answer on the exam. What would this represent? This would represent the cumulative percentage change in sales measured in continuously compounded format. But again, that's not what they asked for. They asked for dollar sales. So to get rid of the ln, you take the e on both sides. So e here and e there. So the e and the ln cancel each other out. So then you're left with sales, and sales equals to that number. And most likely, the sales data would have been given in millions. So this is probably 272.05 million. Now, what are the limitations of a trend model? Well, here's a trend model. It looks awfully similar to a simple linear regression. What's the only difference? Right here. With simple linear regression, the dependent variable is a function of some other independent variable. Like, for example, sales might be a function of GDP. But with a trend model, sales is a function of time. Well, that's not going to change the structure of these frameworks just because you're measuring y relative to some other independent variable or time. That should not change the structure of this framework. In fact, it's the same framework. Where am I going with this? So whatever limitations we came across for regression also applies to trend models. So they're not two different things. They're the same thing. Again, the only difference with trend models is now we're measuring y relative to time. So as I said, the same limitations and assumptions now apply to both regression and trend model. So this is great. Instead of treating these as two distinct things, you just have to know one thing and apply it to both contexts. So what are these limitations? So this would be a review from the previous chapters we did about regression. First of all, the relation between y and, so if you're using regression, it's y versus x. If you're using trend model, it's y versus t. Doesn't matter. The relation must be linear. And this is why I did the visuals. Let me take you to them. There it is, ladies and gentlemen, right? Both of these are trend models. This is a trend model. This is a log linear trend model. You could see that they're both linear. And what's the second set of assumptions that must be met for both regression and a trend model? It's the errors. The errors have to be random. So what are some specifics we're looking for? The expected value for the errors. Doesn't matter if you're using trend or regression. The expected value for the error should be 0. That doesn't mean that there's no errors. It just means that you have some positive errors, some negative errors. When you average it out, it's 0. Second, the variance of the error should be constant throughout. That's called heteroscedasticity. I'm sorry. That means, that implies no heteroscedasticity exists. So the other way of looking at it, when the variance is constant, that's referred to as homoscedasticity, which is the same thing as saying there is no heteroscedasticity. The third thing is there should be no serial correlation. In other words, no autocorrelation among the residuals. So the errors cannot be correlated with each other. And finally, the errors should be normally distributed.